Now we'll go to the gradient with respect to the hidden units. So this portion. So you already see there's a repetition here, right? I don't need to treat each hidden unit separately. I can just have a formula for the hidden unit and then I could compute it for all the hidden units. Okay, so that's what our aim is now. So let's do some simple stuff first and then we'll come back to that. So suppose you have a variable x, okay? You compute two functions from that. One is x square, the other is x cube, okay? I'll call this as y1 and I'll call this as y2. And I take y1 and y2 and compute a z, which is say log of y1 by y2. Okay. Now what I'm interested in is this. What's the answer for this? How do you get this? This is a fair question to ask. y1, y2 are functions of x, z is a function of y1, y2, hence z is a function of x. So I can compute this derivative, I can ask for this derivative. How would you compute it? If, oh, I can't really do this, right? So if this path did not exist, then it's trivial, it's just the chain rule along one path, but now you have two paths. So what will happen? Add them, right? So can you tell me a formula for that? So let me know if this makes sense to you. Okay? Does this make sense? Okay. Now let me complicate this a bit. Let me just do it as y3. Now, what will happen? That's all, right? So you see that if there are multiple paths, you can just add up the chain rule across all these paths, right? That's what chain rule across multiple paths does. Okay. So with this, we'll go back to this figure. So now I'm interested in going to the hidden layers. Again, I'll do this two-pit calculation where I first ask for this guy and then I'll ask for the light blue guy, right? And I'm going to look at one unit at a time. Now what am I interested in? The derivative of the loss function with respect to say dh22, right? The second unit of the second hidden layer, okay? Now what I'm going to say here is exactly what I had written on the previous slide. This was our final function, right, which was z. So z was, so again I've not chosen my variables well, okay, but so we had exactly the same situation, right, which you see here, okay. So we'll just have to sum up the derivatives, partial derivatives across all the paths which lead from this guy to this guy, and there could be as many paths as there can be, but I don't care, I'll just sum across all those paths. In fact, actually here there are not just two paths because we have always assumed there are k classes, so there are actually k of these paths, right? So this is exactly the formula which I wrote on the next slide, right, this one, but just written in terms of the network that we are dealing with, okay. So you can just go back and look at this, but as long as you understand this figure, from my point of view, we can go ahead, okay. So everyone understands this figure, that we just need to compute the derivatives across all the paths and add them up, okay. So now let's start. We again, the same recipe, we'll compute it with respect to one guy and then go towards the gradient, okay. So what is this now? Okay, let me explain, right? So dl theta, there are k of these guys between, right? So there are k paths. So this summation has to happen over k paths. Just as you told me when there were two paths, the summation was 2, 3 paths, the 3, that's k paths, so the summation is over k guys. The derivative with respect to each of these guys and the mth unit, right? That's the index that I am iterating over, okay? And then the derivative of this guy with respect to whatever you are interested in. Okay, that's just there are only two nodes in the path in the chain, but there are k such chains. How many of you exactly get this? Okay. How many of you have a problem? Want me to repeat this? You have a problem? Oh, many of you. Okay. Good. Please do this. So I'm interested in this quantity. That means I'm interested in the partial derivative of this loss function with respect to this guy. And this guy is nothing but hij. That much is clear? Is the jth unit of the ith hidden layer. In fact, this is actually h22. So my I is equal to 2 and j is equal to 2. Okay. Now I just made a case on the previous slide that if you have such a function which first computes some intermediate values and then your final function is computed based on all these intermediate values, right? And now you're trying to find the partial derivative of this with respect to the original input that you had. Okay. So then what you will do is you will sum across all the paths that lead from this guy to the output. Okay. How many such paths are there? You already see 2 such paths here, right? But I am saying there are k such paths because there are some other nodes here which I have not drawn. We have already said that in the output layer we have k nodes, right? So there are k paths. So that takes care of the first bit, that the summation is going to be over the k paths. Okay. Now what is each of these paths composed of? This intermediate value and this quantity that we are interested in. Okay. So first we will take the derivative of the loss with respect to this intermediate value. What is that? That's the unit in the previous layer, or the next layer rather. So I am interested in I. So I'm looking at the unit in the next layer, hence I plus 1, right? Because that's what comes in my path. The next layer is what comes in my path. We have always this special case, right? That this guy feeds into k guys, but all the other hidden units before that feed into n guys, right? So let's just keep that complication aside for the minute, and we'll just look at this case. Okay, is that fine? Okay, so we have agreed there are k paths, and each path is composed of these 2 nodes, from the loss function to this intermediate value, and then from this intermediate value to the quantity of interest. Okay, and why is this I plus 1? Because the next node in the path, right? I am at the ith layer, so I'll be feeding to the I plus 1th layer, right? And in fact, I'll be feeding to all the nodes in the I plus 1th layer. That's why I'm taking over all the k paths, right? And then that node, which is this node, with respect to the quantity that I'm interested in. Is this clear now? Right? This is very similar to the toy example which I did. I just have k paths now instead of 2 paths there. Is it clear now? Sure? Okay. Fine. So let's move ahead. Now, which of these quantities do we already know? Is there any quantity that we know? This one, right? Why? Because in this spatial case, I plus 1 is actually equal to L, right? Because we are feeding into the last layer, and we have already seen how to compute the partial derivatives with respect to the last layer. So this quantity is known. We don't know this for the generic case yet, but we'll get there. But for this spatial case, when we are feeding into the last layer, we know this. Does everyone get this? Okay. Now, do we know this quantity? So what you have told me is that we know this quantity because that is what we have computed in the previous module. Do we know this quantity? We have to compute it. Can you compute it? Okay, let's just do it, right? So let's assume that this hij that I'm dealing with is actually h22. Okay, fine. Now, what is ai plus 1 m actually? Which are the elements there? a31 and a32. I'm assuming that I only have 2 units in the output layer. Okay, so my m is equal to 2. Now, is this fine? This is how the next layer is related to the current hidden layer, plus biases. Okay. Now, what am I interested in? One of these guys. Okay. Let me take one of these guys. So, can you tell me what is A31? First row multiplied by the first column. There is only one column, right? Plus B21. Okay. Sorry. B31. Okay, okay. Yeah. Okay. Fine. Now let me just clarify something. What is this in terms of variables I, J, K, M? What is this? Is this I? Is this J? Is this K? Is this M? This is I plus 1. Right? Okay. This is one of the M's that I am dealing with. Now I want the derivative of this with respect to H, I, J. Okay, in fact I want it with respect to H22, where this is I and this is J. Is this clear? What's this derivative? W312. Everyone fine with this? Okay. Now help me find this. What is this? I, J, K, M, I plus 1. What is this? This is coming from the M. How many of you see this? Because that's the unit that you are connecting to, and this is J. So what's the formula? How many? As many as the number of neurons in the next layer. A bias will be connected to all the neurons in that layer, right? Everyone gets that? Right? There are only 2 units, so there will be only 2 guys. Okay. So what's the formula for this? W I plus 1 mj. Everyone comfortable with that? Okay. Fine. You can just go back and look at this, and it should be clear, right? So whenever you're dealing with vectors and matrices, right? If you're really good at it, you can imagine the entries and figure out what is happening. If you're not good at it, don't be lazy. Just work it out, right? You just need to write down this product, and at the end, remember everything is always element wise, right? You're never dealing with a vector or matrix. You're just dealing with the individual components of them. So you should always be able to compute these derivatives or partial derivatives with respect to the individual components, and that's exactly what I did here, right? So if you just work it out, if you just write it out, then you'll always get it. If you can't, but eventually try to get to a point where you can just visualize it. But if you can't, at least try to work it out, okay? So this is what it will look like, okay? Now, consider these 2 vectors. One is this vector. What does this vector look like? This is a collection of all the partial derivatives. So this is just a collection of all the partial derivatives, nothing new, we have already seen this. Now what is this vector actually? In fact, I have started with a matrix and I'm saying look at this vector. What does this mean? This I plus 1 is just the layer in which the matrix is, right? So that index we don't really care about. For a matrix, what we care about is the I comma j index, okay? Now what does this dot comma j mean? All the i's belonging to j. That means the dash column, jth column. Everyone gets this? This is all the i's or all the entries belonging to the jth column. So it's effectively just the jth column. So it is 1 comma j, 2 comma j up to k comma j. Right? So these are 2 valid vectors. Now tell me, what is this quantity going to be? This is the dash between 2 vectors. Dot product. Dot product between 2 vectors is a summation over element wise thing. Okay, I have said enough. Now try to connect this. This is a very simple match the column that you will ever get in your life. Try to connect this to something which is already there in the slide. How many of you think the answer is this? This into this plus this into this plus this into this, and just write it as a formula, you will get this. Everyone sees that? Okay. So now I have a compact way of writing one of these entries. Okay. One of these guys. I have a compact way of writing this. It happens to be the dot product between 2 vectors. One of them is the gradient, but do I know this already? Do I know this quantity already? In this special case, yes, because I plus 1 is equal to L, and that I have already computed. This of course I know, right, because these are the weights that I am dealing with. Where do I go from here? This dot. Yeah, it means anything from that column. So that means the entire column. No, these are weights, right? So this is a weight matrix. It has columns and rows. So I'm talking about the jth column. So I fixed the value of j. So I'm talking about the jth column, but I'm not telling you a given ith entry there. I'm just telling you all the entries there. That just means the jth column. We can take this offline. Okay, this is very simple, but I'll take it offline. Okay. Now where do I go from here? Huh? I plus 1? Okay, no, in this specific case, are we done? Where are we right now? With respect to 1 unit. Where do we want to go? The entire thing. So what is the quantity that I'm interested in? Gradient with respect to, always say with respect to, h I, right, where I is 2 in this case, the spatial case. Okay. What is that going to be? Collection of all these guys that you have already computed. Okay. Now simplify this. What is this? First column of the matrix multiplied by the same vector. The second column of the matrix multiplied by this vector. The nth column of the matrix multiplied by this vector. This reminds you of something very, very difficult. This is a very, very complicated matrix multiplication. Right? First row of the matrix multiplied by a column. The second row of the matrix multiplied by a column. How many of you get this? Right, so this is, can you tell me what this is? Wi plus 1 transpose. Perfect, right? So now you see that this entire quantity we can compute in one go by using a matrix vector multiplication, right? So that's what I meant when I was saying that we should not be doing these individual computations, but be able to compute that at one go, right? So now we can just do this matrix vector multiplication and get this entire quantity. Okay. Now what is still missing in this module? So what is the spatial case that I have assumed? I told you that I already know these quantities, but only if I plus 1 is equal to L. I need to tell you this in the generic case. Okay. So we are almost there, except that I don't know this when I is not equal to L or I is less than equal to L minus 1. Okay. That's the case that I am looking for. So that's again very simple. Again, what will I do? I'll compute it with respect to, okay, what is this? This is the guy that I'm interested in, the generic I, not the Lth one, right? The generic I. This is what the vector looks like, the gradient vector looks like. I want each of these guys. Okay. Now I'll take one of those and I'll write it as this. Okay. What am I doing? I'm saying that I already have the entries up to here. Okay, at a very general level. Even here I could have said the same thing. Remember that I had said that the output layer you can always write as HL, right? So even at the output layer I could say this. This chain rule always holds. How many of you agree with that? I want to go from the loss function to one of the lighter blue guys. So I'm saying that I can go through the intermediary dark blue guys. That's all I'm saying. I've just compressed this entire path into up to the dark blue guy. Remember I had said earlier that I'll be compressing these chains. Is this clear to everyone? Okay. Now how many of these quantities do you know? The first one is what we computed on the previous slide. Okay. The second one looks very difficult. Sorry. So Hij is nothing but sigmoid of Aij or any non-linearity of the Aij. So I can just write this derivative as, I'll just write it as sigma prime, okay, or G prime. Is this fine? Okay. Okay. Now I have it with respect to 1 unit. What will I do? Go to the gradient, fit it all these values. Now simplify this. What is this? A vector, right? What is this? Another vector. There is a one-to-one correspondence between them. So you have two vectors and you're doing a one-to-one multiplication. What is this? How many of you say dot product? Dot product is always a, what is the output here? Vector. Can it be a dot product? Can it be a dot product? No, please, emphatic no. No, okay. So what is it going to be? An element wise multiplication, and this is how you denote that. Okay. So what is this called? the Hadamard product, right? So this is every element of one vector multiplied by the corresponding element of the other vector. Okay. So now again, the entire vector we can compute at one go, right? When I'm teaching this, I'm telling you how to compute one element and then go to the gradient. But when you're going to implement this, you're just going to compute the gradient at one go. Is that clear? Okay.